One is depicting the sort of static information about the data, and another one dynamic. But the two perspectives are related in some way. So let's say you change the name of a class in one perspective, you would expect that to be reflected in the other perspective as well. So there's this kind of idea of entanglement going on, which I'll talk about. The idea sort of happens not just in computer science. It's a very sort of general idea. In sort of general architecture of buildings, you might have sort of a plan view of your building or elevation view, and the two are inextricably linked. Okay. So you might wonder. Okay, so we've said that one of these view model BXs is very suggestive, given the operations that are at play here, that a state monad would be a good candidate to implement. So perhaps we have two views. How about two instances of the state monad? So let's see. So what that means, if we have two instances of state, we have two pairs of view update operations. So let's say we have, think of A and B as memory cells, if you will, and they're entangled in this way. So these are the same view and update operations as before, but they're now parameterized by their respective memory cell, if you like, A and B. And so you might ask, what are the laws now of this two view, one model VX? Well, so each view update pair. So in particular, the view update, view A, update A. That's going to be an instance of the previous view model VX, which we said is going to be the same laws as the state monad minus the put one. And similarly for view B, update B as well. So we have effectively two algebraic theories here. And then you wonder, well, would there be any extra laws? So at the moment, there's nothing to say how the two interact with each other. So that's a natural question to us. Okay, so let's see how we might implement entangled state. So you might think, we said, sorry to go back and forth. So we said two instances of state, might be the way to implement this sort of multi-view model VX. So let's try this. Let's try state monad on pairs A and B. It's like a Cartesian product. And this is a kind of the expected implementation of the view and update that we saw on the previous slide. So these gets, these gets, binds, returns are with respect to the state monad on pairs, right? So, so how do we implement view A? Well, we do a get that gives us a pair of A and B, and then we return the A. Update B, we will update B with S. The get gives us a pair AB, and then we put that S. Okay, so given this kind of natural implementation, we actually find that it satisfies too many laws actually. So in particular, if we implement this view model BX in this way, with this state monad on pairs, we get commutativity of update A and update B. Which is to say, if I write to memory cell A, think of mental picture as a memory cell, and then follow it with a write to memory cell B, that's the same as doing it in the opposite order, so writing to B and then writing to A. Which would make sense if they were independent, but the picture you want to have in your head is something like this. think of the model as two memory cells, if you like. So I've called them A and B here. So you would expect commutativity of update A and update B, if they were distinct memory cells. There's no reason to expect why. There's no reason to expect why updating A should affect B and vice versa. But because we're saying they're entangled, which is the situation with Bx, I'm going to represent entanglement with this squiggle. Then effectively, what's happening is when you do an update to A, it's also going to have an effect on B. So that's the reason why it doesn't commute. And in fact, it's not just with updates as well. I mean, if I do an update to A, it also won't commute with a get with B either, right? So if I update this, if I update A, then that's going to have some effect on B, and if I then I've got a view on there, sorry. Yeah. If I then do a view on B, then that's going to have taken account of the update A. So, so clearly, I can't just reverse the order of these two and expect them to be the same. And that's because they're entangled. So that's the phenomenon going on here. Okay. So I think maybe the key thing to note about the analysis so far of this entangled state problem is the equations. The laws. They really play a very central role here, and because of that, it's quite natural to consider this problem in terms of the algebraic view of effects, much like the first talk in the session. So, what do we already know about combining effects in the algebraic setting? So, I mean, there's a paper by Gordon Plonkin and John Power on combining effects, Sun and Tensor, and Highland, sorry, as well. Okay. Oh, so Highland instead of.
It's all three.
Highland plus Plonkin.
Okay, so right. Yeah. Better change that. So I'm going to do massive injustice to that paper by summarising it in 2 bullet points.
I'll do a bit more later.
So effectively, we know about 2 constructions when we're talking about combining effects in the algebraic setting. So there's a sum construction. These are, by the way, these are the constructions on Lauver theories, which we've already heard about. So effectively, what's happening on the sort of equational level, the sum will take a kind of union of theories, which is to say, I have 2 algebraic theories, and I combine them by taking all of the operations from one, or all of the operations from the other, and I also take all the laws with them as well, so all of the laws of the first and the second, to make one big amalgamated theory. And the tensor is a similar kind of thing going on there, except it also adds some additional laws as well, and those additional laws state commutativity of operations of one theory with the other. So, I think examples are probably best here. First example, is something we've seen already actually. So remember the implementation of entangled state that we had. So that was state on pairs. So that can be seen as a tensor product of state with itself. So we said that, for example, in this setting, update A does commute with update B, right? So, which is why it wasn't a good implementation for the BX setting, but that's what that is. Okay, let's look at another example, which is also quite sort of statey, and I will ask you to recall the maybe monad, which I perhaps should have called So usually it's called nothing, so nothing for one and just for the underscore. So what would happen if we combine state and maybe together? Well, let's compose them this way. And what we get is something we can call backtrackable state. Backtrackable because, well, if you look at this type signature, which is what you'll get if you compose these two in this way, I mean, you'll either get, if you think of this as a state transforming function, if it fails, you'll get nothing. In particular, anything that was changed in your state, is also not returned. So you can think of any updates you've made to the state to be reverted or discarded. So yeah, the interesting thing is this combination is also tensor as well. So this is another result. So so explicitly, what is this? So this construction here is the algebraic theory that is all of the operations of state. That's again put under all of the four laws, and maybe, which is just one operation here. And what are the laws? Well, we said all the laws are for get and put, and there's also an additional law due to tensor product. And I've written it in terms of monadic bind here, but essentially what I'm saying is if I have a computation followed by nothing, then followed by a failed essentially, then that's also going to be a failed computation. Reason being, let's say this is an update. If I write something and then it fails, well, I mean that's the same as discarding whatever was written. So this is exactly a backtrackable sort of behavior. So interestingly, if you compose them the other way around in terms of monads, you get a different kind of behavior, which is you can think of as global state. So in this case, if you did get a fail in computation, any changes that you did make to the state will also be emitted as well. So in the monadic setting, this is just simply composing the functions in a different order. But in the algebraic setting, it's a bit less clear, at least to me, what this means. So I have a hunch it could be the sum, and I've been speaking to my postdoc yesterday about it, but we haven't. It is a sum, right? Okay, cool. Let's talk about it. Let's look at one more example. So if we take non-deterministic choice, which is a binary operation, and it satisfies the laws of commutativity, idempotency, and associativity. So these are semi-lattice, basically, theory. This gives rise to the finite non-empty power set monad, which in Haskell it is normally approximated with lists. Let's also introduce probabilistic choice, which is a bit more complicated. So I'll just say that this is some notation which takes two computations for P and Q and behaves as P. So PWQ behaves as P for probability W and Q with probability 1 minus W. So there are some sort of weird, complicated laws which I've omitted here. And what I'm really interested in is how does non-deterministic choice and probabilistic choice interact with each other. So there's an example. I mean, if we have a program coin which represents a fair coin toss, and arb, which is an arbitrary non-deterministic choice between true and false, would you expect these two programs to be the same? The only thing that's different about these two programs is the order in which I've done the choices. So one is non-determinism first, and then probability, and the other one is the other way around. And the answer is they are different, and that's because the non-deterministic choice in the second instance is in some sense allowed to depend on the results of the non-deterministic choice, whereas that wouldn't make sense for the or the other way around. Otherwise, if coin could depend on arb, say, then coin would no longer be a fair coin toss. You can prove this that they're not equal by equational reasoning, which you can find in Just Do It, a paper by Jeremy and Ralph friends. So I think the really interesting thing about this interaction for me, though, is that it satisfies an additional distributivity law, which relates how the two choice operations interact with each other. So this is a bit different from the previous equations, because it's not a commutativity equation, but a distributivity equation. It says that probability distributes over non-determinism. And it turns out that this combination of two effects is a construction called distributive tensor. Again, it arises from a paper by John Power. Discrete law Beer theories, I think, is the one you want here. So what we've seen really is that there are not only two constructions. There's at least three constructions on law Beer theories, which have application in computation. And there's another example of non-deterministic choice, which I don't have time to talk about, but essentially this is interesting because it's also an example of distributive tensor, but it distributes in both ways. So, I mean, having considered all of these constructions on effects when looked at algebraically, we can come back to the question of entangled state and ask, can it be explained as something like this, as a combination of algebraic theories? I don't know the answer to this, but I can. But we've just shown that these constructions do exist, and whether this is an example of one that we've considered already, or is it something quite different? I don't know. So another interesting problem really is how these distributive tensors are related to the monadic setting, distributive laws. That's more work in progress. Yeah, that's pretty much it.
Do we have any pressing, very, very short question for the break?
Not very sure, but do you know some work called operation transformations? Because they are the people who design like Google Docs and so on. The underlying technology of Google Docs is called operation transformation. But one of the things they want to do is they want to make sure if I add a Google Doc, simultaneously you add a Google Doc as well. Then they want to make sure that these Google Doc, in my copy as well as your copy, both converge. So this problem is related, and then the core idea they had was thinking about lifting each operation, like editing operation, into an operation on operation. So lifting it to a higher order operation, and it looks like they have some way to solve it for some particular scenario, but not in general. So I just say maybe worth to comment.
Thanks.
Okay, I just have one small comment, which is, you talked about sums and tensors of theories, and I'm not an expert category theorist, but when you see one tensor product, there are often many more lurking around. So, maybe you should get your hands dirty and make up some more ways of combining theories.
Sure.
I was going to suggest something along similar lines. Early on in the slides, you made the claim that, we can't have Kwok because these two guys are entangled. I think the correct answer is these two guys are maybe entangled. It depends on what they are and how you set it up. And so therefore what you really want is maybe an algebra of tensors, where you can say, well, I have some components that are entangled, some aren't, and then compositionally I can build up the particular relationship for particular, two choices of views and describe the degree to and the locality of the entanglement. Right? So instead of having a once and for all solution, you want an algebra solution.
So No announcement. We'll start at 2 o'clock as scheduled.